I love being introduced with shitty puns, so thank you. My name is Lynn Root. I am a staff engineer at Spotify, and I've worked there for about 7 years now, and I am based in New York. As a quick aside, I kind of prefer not to do live Q&A, so if folks could just find me in Slack instead, I'd be happy to answer your questions and chit-chat there. So the intent of this talk is to walk through the design and architecture of a suite of libraries that my team built in the past year and a half, specifically to support audio intelligence research. So what exactly is audio intelligence research, you might ask? So paraphrasing our own researchers, audio intelligence research at Spotify advances the state of the art in understanding music at scale to enhance how it is created, identified, and consumed. So examples of this include algorithms for automatically finding musical properties like beats, tempo, and pitch, or detecting cover songs, identifying language, and plenty of other awesome things. Our research team also publishes data sets and papers describing their work for a broader community to use. But as an infrastructure engineer, the main focus of my team is on the at-scale part of audio research. We want researchers to spend the majority of their time thinking about their research rather than managing code deployments or writing libraries for distributing work across multiple machines. So in order for us infrastructure engineers to understand the problem, we wanted to look at the way researchers work. So in general, audio researchers start with a single audio file or maybe some audio metadata and apply some transform to it. And this produces some useful data about a song. So for example, the positions of beats in a song and its tempo. As you might imagine, most research builds upon other research. You might have the same researcher using their own research or research of others. So for example, you might have the beats and tempos of two songs, and then you can write another transformation that finds the optimal way to mix them together. You could then chain multiple transforms together with one depending on the output of another. In other words, a lot of this work can be represented as a directed acyclic graph. Once researchers are happy with the algorithms that they've developed, they will want to find a way to run them on many, if not all, of our catalog, of our songs in our catalog. So for example, in order to make it possible to mix any two songs together seamlessly, you'll need to find beats and tempo for all songs. So now that we understand a little bit of their workflow, let's talk a bit about what researchers need in concrete terms in order to put their research into production. So as I've mentioned, we essentially have a graph of transformations. The natural question that follows is what types of execution over the graph are most useful for researchers? And so as it turns out, there are two forms of execution, what we refer to as top-down and bottom-up execution. So with top-down execution, every transformation in a graph is run for every audio file submitted to the graph. So as an example, we have a graph of transformations here. And then a reference to an audio file is submitted to the work queue of a node in the graph. It can be the apex node or any node within the graph. The transformation in the node is run, and the audio file reference is then submitted to the work queues of its child nodes. Once those finish, they submit work to their child nodes, and so on, until everything below the originating node where work has been submitted has been executed. So that essentially is top-down processing. The other mode is called bottom-up. It's not always efficient or necessary to run transformations for every node in the graph of a file. Sometimes you just want to run a single transformation, which sometimes means just running its parent's transformation to fill in missing dependencies. In this mode, the missing dependencies for a particular transformation are recursively created. So as an example, again, we have a graph of transformations. We submit work somewhere on the graph, and we check to see if we can run it. Let's say that an upstream dependency is missing. So then we'll need to submit the audio file to its parent's work queue. And then let's say those dependencies are also missing there. So work again is submitted to its parent. When work finishes on this node, it essentially resubmits work to the child node. But work is only submitted to the child node in the path of the originating node. Other child nodes are not triggered. This is particularly useful when work needs to be rerun on just one branch of the graph. And so, so production requirements so far include both top-down and bottom-up execution. And now let's take a look at requirements of the transformations themselves. First up is Python. Python is a very popular language with audio researchers. Most of them are not trained as software engineers and are most fluent in Python. Not only are most audio processing dependencies written in Python, but recent audio research has started to include machine learning, yet another domain that's dominated by Python. Secondly, researchers need control over the environment in which their code runs in order to be reproducible. And so this typically means being able to install the exact versions of dependencies that are needed. And then custom environments also allow for researchers to make use of non-Python dependencies like C libraries and extensions if needed. Next, ideally, audio data should be processed as soon as it arrives rather than waiting for a specific time window to close. So for example, we want to extract features from a newly released song as soon as it's possible so that track can be included in our algorithmic playlists. And we essentially want a streaming system that listens for inputs and reacts to them rather than a batch processing system. Another requirement is to avoid duplicate work. Transformations can be expensive and may only need to be done once. Therefore, researchers want a system to have existence checks on the output of transformations that make it possible to avoid reprocessing the same data with the same code. The last requirement is scalability. There is the occasional need to run an entire graph of transformations on the full catalog of audio data. So whatever tooling we build to support researchers, it would need to include the ability to scale processing on the graph transformations to tens of millions of songs. So to review real quickly, researchers need tooling that supports top-down and bottom-up execution and a directed acyclic graph of transformations. They need to be able to write their transformations in Python, as well as have control over exactly what's installed in the runtime environment. They also want to avoid rerunning the same transformations on the same audio data, and they want it to be event-driven or streaming rather than batch-oriented. And they need to do that all at scale. So how did researchers originally solve this? Well, we can walk through a few of their early approaches. At first, researchers started with a graph of Dockerized services that listened to pub/sub queues for work, which they called the music intelligence pipeline. Each service handled a single transformation with an input topic to receive work and an output topic to signal to downstream jobs that work has been done. This met requirements. It supported Python, enabled customized environments, allowed for idempotent work, was streaming, and could be scaled. But it took a lot of effort to maintain, and it wasn't exactly cost-effective. Around the same time that researchers were developing the music intelligence pipeline, Spotify was busy migrating to Google Cloud Platform. Apache Beam running on Google Cloud Dataflow became very popular within the company for batch and streaming processing workloads, particularly with Shio. And so what Beam gives us is a Python SDK and a mechanism to customize the runtime environment with the needed non-Python libraries and tooling. And this meant that it was possible to replace those microservices in the music intelligence pipeline with streaming Apache Beam jobs running on Dataflow. And since Dataflow is a managed service, this made deploying and scaling easier for researchers. That said, the graph of streaming Dataflow jobs is still complicated and error-prone to maintain. So on a single graph or transform, there are many steps to take when the code changes, when the data changes, or required changes to any aspect of the job's configuration, such as a change to worker type. Now, this isn't great for a research flow where reproducibility of results is very important. There's also no built-in support for how to execute a graph of jobs. We want that top-down and bottom-up execution. And we did look at off-the-shelf orchestration solutions such as Luigi and Airflow, among others, but they're focused on batch and therefore were not a good fit for streaming jobs. So to address the missing pieces, we formed a team to support this workflow. And we ended up developing a tool called Clio. So at Spotify, we have a tendency to name our software after Greek mythology. The name Clio comes from the Greek muse Clio. She was a muse of history and lyre playing. However, we dropped the E to avoid confusion, which then made it a nice complement to our sister open source library, Shio. And so Clio is meant to provide the user-friendly layer of abstraction for executing and managing a DAG of transformations. It's also an opinionated approach to streaming Beam jobs in Python on Dataflow. It's particularly tuned for audio processing, but one can certainly use it for a more general Python streaming use case. It provides a more Pythonic API for writing a Beam job, allowing researchers to focus on the core of their problem rather than worry about pipeline configuration and execution. It supports both top-down and bottom-up execution of pipelines that may be owned by multiple teams across multiple Google Cloud projects. It includes a ping mode to follow a path down a DAG without triggering work in case one needs to debug a particular path. It's also optimized to not redo work, but allows the user to do so if needed. It makes use of the Apache Beam portability framework, allowing folks to create Docker images of the exact environment needed, including non-Python libraries. And then it could be easily deployed via CI/CD with no drop to messages, allowing for quick iteration. So Clio isn't exactly a single thing. It's more of an ecosystem. From the point of view of the user, they mainly interact with our CLI component. So users will pip install the Clio CLI, and then they can get to work immediately. Running Clio job create will generate the necessary files and create the resources needed in Google Cloud, and then produces like a hello world-like example of a transform. Also available is running Clio job verify to make sure that all the required job-related resources in Google Cloud are available, like the pub/sub input and output topics, storage buckets, and the CI/CD setup. The user also has a few testing-related commands available to them. Clio job test will run the user's unit test for a transform. We have Clio job audit, which will inspect a user's transform to see if there's any anti-patterns being used, like how resources are being cleaned up. So for instance, improper use of temporary files using up disk space, or long-lived TensorFlow sessions hogging up memory. And these are very rudimentary, but we definitely want to build these up. The Clio job profile command will profile memory and CPU of a job's transforms, helping users pinpoint any undue resource usage or bottlenecking behavior. And this also helps figure out what kind of machine type to use when running the job on Dataflow. Once the user is happy with the job setup, they can run Clio job run, and this deploys everything needed to Dataflow and kicks off the job, or if desired, they can run locally with the direct runner. And when the job is running, either in Dataflow or Direct Runner, users can then run Clio message publish with the desired audio IDs, and messages will be published to the job's input queue to kick off work. And finally, they can also see job logs locally once it's running on Dataflow via Clio job logs. And now if we peek under the hood a little bit, we can see a bit more of the heavy lifting being done. So either in the machines or from a CI/CD setup, when a user invokes Clio job run, behind the scenes, Clio builds a Docker image that will be both the worker image on Dataflow as well as the driver, the part of Beam pipeline that launches and kicks off everything. User-defined transforms, configuration, and Python and system-level requirements are installed in this image. And then once built, Clio job run runs the container with additional set required for kicking off the job, like environment variables pointing to necessary credentials. Within that Docker image, we also have a tool called Clio Executor. And this is simply a tool that actually runs the pipeline with the user's configuration. It's the driver. And so at this point, the built image then gets uploaded to Google's container registry. And then Dataflow essentially takes it from there. Dataflow will orchestrate the pulling down of that image, spinning up the needed worker machines, and running containers across those workers. When generating work, Clio message publish will publish Clio messages to the job's configured input topic on Google PubSub, which then Dataflow distributes across the workers. Logs are made available on Stackdriver by default, and then Clio provides custom user metrics that are then available in Stackdriver monitoring. And then you can also just tail the logs locally via Clio job logs. And so all of this is some of the heavy lifting done that the user doesn't see. It's done by two parts of the ecosystem, the Clio CLI and the Clio Executor. There's a third part to the ecosystem, the Clio library itself, and that actually defines a bit of the architecture. So zooming in a bit, if we take a look at what a Clio job actually is, it's the user's transform code plus configuration and the Clio library, which I'll get to a bit more in a bit. The Clio job consumes messages from PubSub, and inside the message is a unique ID that refers to an audio file. So essentially, a message is viewed as one unit of work. There's then some pre-processing work that Clio does. It unpacks the consumed message and decides how it should be handled. Should this job actually be doing work for this particular audio ID? Does the required input exist? And then I'll dive deeper into that in a bit. But then after pre-processing, if all is good, it is then passed off to the user's transform logic. Within the user's transform code, they can then securely download the input audio from Google Cloud Storage. And then the user's transform will process the audio however it needs, and then upload the results to another bucket in Google Cloud Storage. Once the user's transform is done, there is some post-processing. There isn't that much, just handling if the user's code has errored out. And if not, then just reserializing that data as a Clio message to then be published to the job's output topic. And that publishing signifies that the Clio job is done processing that particular work. So zooming out a little bit, you can think of a Clio job sort of like a backend service where instead of an HTTP request, it consumes a message, and then instead of an HTTP response, it publishes a message. And so these DAGs, these graphs, can be formed by connecting PubSub topics where the output message signals a unit of work has been done and is ready for a downstream child to process. Going back to the handling of the message and pre-processing real quick. When the team behind Clio first organized, we didn't know if the team would be permanent or not, which influenced our design decisions. We shouldn't build any service that we might not be able to maintain because we don't know if we're going to exist. So it was imperative that we be stateless. And that's evident in the contents of the Clio message that's passed through PubSub. So as I said before, the Clio message is considered one unit of work that a transform or a pipeline needs to handle. It contains a unique ID that refers to an audio file. Then this is the data that the user's transforms work with. The Clio message also has metadata that a user's transform doesn't see. Its metadata influences how Clio should handle this unit of work during pre-processing. And I have a handy dandy flowchart. So when a Clio job consumes a message, it essentially needs to figure out if this is a bottom-up or top-down execution. So it basically sees if this Clio job itself is in the downstream path for this message. If not, then it's a bottom-up execution and it's not meant to handle this piece of work. Clio will then just drop the message and stop handling it altogether. However, if this job is in the downstream path, or if there's actually no downstream path at all, meaning that it's top-down execution, then Clio moves on to the next check. which is this message in ping mode? And ping mode just follows a graph obeying top-down, bottom-up execution, but doesn't trigger any work. So if it's in ping mode, the message then just gets passed through and published to the job's output topic. If not, then Klio proceeds to the next check. Does the output data for this unit of work already exist? So we want to avoid spending time and resources on work already done. So if output already exists, then it goes on to the next check. Should we actually force work to be done? Maybe another version of the transform is being used, so we want to redo all past work. If not, then the message is not worked on and is published to the job's output topic. If it is in force mode, or if the output data doesn't actually exist, then Klio moves on to the next check. Does the input data actually exist? If it doesn't, then Klio will add itself to the list of downstream jobs in a message metadata, and then publish to the parent's input topic. Klio then drops the current message. Since there's no need to hang on to it, it will actually get a new message once the parent job is done and input data exists. And so if input data does exist, then we're good to go onto the user part of the code. And so Klio will then invoke the user's transform, and so work can be applied. So I know the design and architecture of Klio is super interesting. I can hear you. But now I'm sure you're all thinking, show me some freaking code. So I'm going to demonstrate this with an automixer algorithm. It's an open source algorithm that's not by Spotify at all. And this will take two different tracks with different tempos and blend them together in a way that seems seamless. Essentially what a DJ does when playing one track after another. So we have two input tracks and a single output track. The transform itself will find beats and tempo of each track and then find the optimal tempo for matching between both tracks. The transform will then find the crossfade region, and in that crossfade region of both tracks, it will either speed them up or slow them down appropriately so that they match. And finally, it will concatenate the adjusted song segments together into one file. And so I'll first show this job with like plain vanilla Beam without Klio. And then I'll compare the two to hopefully show where Klio can shine for users. So we first have the following files. The job requirements file defines a job's dependencies. We might also have a Docker file to have a repeatable and clean environment. The mixer.py and the track storage.py contain the transform logic and helper tools. And then run.py actually sets up the pipeline for execution. If we take a look, it's a lot, and you're not supposed to see this code. It's just like too much to read, right? It's about 125 lines of code. And again, this is not actually the mixer code itself. It's literally all the boilerplate related to configuring, downloading, uploading, and checking if input and output data already exist. And then if we're running on Dataflow, maybe you would first build and upload your worker image, and then run.py to kick off the job. However, Python dependencies on a developer machine can get quite messy. Running a pipeline this way can be problematic because your local developer environment might be different than the worker image you just generated. So a solution to that is executing the pipeline within the worker image itself, like so, where you would run the image with the appropriate flags, mounts, and environment variables. And that is a lot, but it can be easier. So now we're going to Clioify it. So there's not much difference in the anatomy of the job when looking at the directory structure. We do have a new file, one that contains pipeline configuration. And then if we take a look at this run.py, you can see that it's a lot smaller. It's actually only 30 lines of code. And this is where Klio essentially abstracts away any boilerplate code and configuration for the user. As well, it is a lot simpler to run. No need to worry about different Python environments or remembering all those Docker flags. If we take a closer look at the Klio job, a user will need to import some decorators. And this decorator does some behind-the-scenes serialization of the Clio message. It also gives the users access to job configuration, logging metrics, as well as sets up testing and profiling environments. To show what else Clio does, we can take a look at the YAML configuration. First up, we have the job name and the pipeline option. And both of these are usually portrayed as parsed arguments from the command line using Python's argparse module. Moving all these into configuration allows us to have everything in one place, as well as make it easier to deploy the same logic using different configuration with no code changes needed. Next is all the Clio-related logic. We separate out events from data, where events are essentially triggers. Each event is a Clio message, and each Clio message should trigger some sort of work to be done. Here we have our own subscription to our parent's output topic, and we've also defined our own output topic from which other jobs can consume. Data points, the data points to the Clio job or allows the Clio job to find where the actual audio or otherwise binary files are. Each Clio message should have an ID that points to a file defined in the configured location. And here we read from our parent's output bucket in GCS, and we write to our own output bucket. So behind the scenes, Clio will construct a pipeline object with the given options that will first read IO from the configured subscription, and we'll check if output exists by constructing the path with the configured input location, the ID given in the Clio message, and the configured file suffix, and then actually look it up to see if the file exists. Then check if input data exists by doing the same thing, construct the path based off of configuration and the Clio message, and look up its existence. If all is good, it will then call the user's code, which is essentially a subset of the entire pipeline, and finally write output to the configured topic. So with a little bit of configuration and some helpers, Clio can take this and allow users to just care about this. So overall, Clio strives to simplify defining Beam pipelines for users. By removing configuration from code into a separate YAML file, it allows the jobs to be both portable and quickly iterated upon. There's no need to make code changes or rebuild and push entire Docker containers when you're just wanting to use a higher CPU machine. Folks don't need to worry about differing environments when launching the job, or remembering to include their deployment credentials in the Docker container at runtime, but not within the built image itself. And then Clio takes care of the user's DAG so that the user can just worry about the transform logic. All right, so on to some takeaways. First up, what worked? So the stateless architecture gives us a lot of flexibilities. Maintainers are decoupled from users, so we've largely been able to quickly iterate and add new features without breaking changes. And despite the fact that this was initially developed for a research workflow, product-focused teams have wanted to use Clio because it makes working with streaming data flow pipelines in jobs so much easier. And then we're also able to process our entire catalog, tens of millions of songs, in days rather than weeks. From a technical perspective, there wasn't much that was quite difficult for us. We were working with experimental features, or not quite GA features, so we had some little hiccups. But the biggest headaches were actually from pickling errors or dependency conflicts. And then understanding a job's memory footprint was quite difficult. But then we added some basic profiling capabilities within Clio itself, which helped a lot. And finally, what's next? We're going to be focusing on adding batch support, as well as develop an understanding of scaling Clio for bigger workloads. At the moment, it's a bit of a hand-tuned process. We have a lot of trickier design questions that we want to address as well, like how to manage multiple inputs and outputs, and how to approach end-to-end or integration testing. And in the longer term, we want researchers to be able to use Clio easily from within Jupyter notebooks. And finally, we will be open sourcing Clio, hopefully by the end of this quarter, if all things go well. So thank you for listening. My corporate spiel, pardon me, Spotify is hiring. So check us out on spotifyjobs.com if you're interested. As I said before, I'm certainly happy to take questions and chat further, but on the Slack channel. And so, yeah, thank you very much.
Thank you, Lynn. That was a very interesting talk. Thank you for sharing. Looks like Clio is a nifty little tool for your internal users. And you actually answered one of my questions that I had already. If Clio was going to be open source, so that's really cool. And as we discussed, yeah, you will hopefully join us now in the Slack channel and answer some questions there. And I'll make the floor available for the next talk. Thank you very much.
Thank you.